A very good afternoon to all. My name is Alfred Vivek and I work as an assistant professor in the Department of Electronics and Communication Engineering, Vidyavardhaka College of Engineering, Mysuru. And today, in this session, I'll take you through the analog circuits part of GATE 2021 syllabus. But before we begin, let us have a quick look of the syllabus for analog circuits part. What is prescribed for GATE 2021. So we have topics on diode circuits, in that clipping, clamping, and rectifiers. Then we have some topics from bipolar junction transistors and MOS FET amplifiers, their basic biasing, coupling, and small signal analysis, and also the frequency response. Then current mirrors and differential amplifiers are also included. The last part is the op-amp circuits, in which amplifiers, adders, differentiators, integrators, some active filters like low-pass filter, high-pass filter, and band-pass filters, non-linear circuits such as Schmitt triggers and oscillators are included. Most of the topics that are prescribed for GATE 2021 syllabus for analog circuits is very. But some of the topics which you should not be skipping are diode circuits, basic BJT, amplifiers, and op-amp circuits. In these topics, you can score maximum marks. So I'll put a check mark. You should not be leaving these topics: the diode rectifiers, op-amp circuits, and the BJT amplifiers, BJT and MOSFET amplifiers, biasing, and small signal analysis. So you get more number of questions from these parts. So you have a good chance of scoring better if you study these topics thoroughly and then go to the examinations. Okay, let us not waste much of the time. Let's go and dive into the syllabus. The first topic what I'm going to take is the diode circuits, because for the want of time, I'll not explain in detail about the diodes, but rather I'll take some of the typical questions that are asked in various GATE examinations, and we'll have along with the problems we'll have a discussion, and let's try to understand and solve some of the problems. So the first example what I'm going to take is on this topic, that is the basic diode current equation. Before attempting this question, let me explain a little bit about the diode. The circuit symbol for the diode is like this. This is the circuit symbol for the diode. And this diode has two pins, two terminals. We have anode this side and cathode this side. It's a unidirectional device, and current can flow from anode to cathode if the diode is forward biased. How can we forward bias a diode? By applying potential difference between its anode and cathode terminals. If the potential of if the voltage of anode is greater compared to the voltage of the cathode, like this. So if I make anode positive compared to the cathode, relative to the cathode, then the diode is forward biased. Ideally, any positive voltage on anode with respect to cathode should forward bias the diode, and current should start to flow from anode to cathode. So the ideal VI characteristic of the diode is something like this. If you make anode less positive compared to the cathode, then the diode will not conduct. It is in off state. Immediately after 0, the diode enters on state, and it allows a huge amount of current to flow. So this is the VI characteristic, typical VI characteristic of a diode for an ideal diode. However, we don't have ideal diode. So for practical diodes, if you reverse bias them, a small amount of reverse current will flow. And once you forward bias, till it reaches its new voltage, the current through the diode is zero, very close to zero, and afterwards it increases exponentially. So the point after which it increases exponentially is known as its knee voltage or its break-in voltage, normally referred to as V gamma. This is also called as cut-in voltage. Cut-in voltage. Okay, this is the behavior of the ideal diode. If the diode is silicon, then this cut-in voltage will be around 0.7 volt. And whenever we have diodes in our circuits, we really don't use this diode current equation to estimate the amount of current flowing through the circuit. Instead, we rely on models. So at least for the gate examination, from gate examination point of view, you should know two models. One is the ideal equivalent model and another one is simplified equivalent model. In case of ideal equivalent model, a forward biased diode, if the diode is forward biased, then it is represented as a closed switch. It is represented as a closed switch. That means current can flow through the diode. Of course, unidirectional from anode to cathode. If the diode is reverse biased, then it is represented as an open circuit or an open switch. So current cannot flow. There is absolutely no current flowing. This is the ideal representation. But for practical purposes, we can use simplified equivalent model. So for the forward biased diode, we make use of this representation. So a diode will have two terminals, anode and cathode. So if the diode is forward biased, then it is represented as a voltage source with the polarity as shown like this. Towards anode, it should be positive. Towards cathode, it should be negative. And the value will be equal to its cut-in voltage. In case of silicon, it is 0.7 volt. And reverse bias, we don't worry much about the reverse biased diode. It is still represented as open circuit. Okay, this is simplified model, simplified equivalent model. If you want more accuracy, then you can go ahead and use the piecewise linear model. For forward biased diode, in the piecewise linear model, what we do is we'll represent it as an voltage source followed by a resistance. So this will be equal to the DC resistance of the diode. So R DC resistance of the diode, and this voltage source value will be equal to its cut-in voltage. This is how we represent a forward biased diode. And of course, for reverse biased diode, we'll use the open circuit representation. This is for reverse bias. This is for piecewise linear. This is the piecewise linear model. So we'll make use of ideal sometime, most of the times, and sometimes in the question, if they say the diode is a practical silicon diode, then you can use simplified equivalent model. So with this background, let us try to solve the first question, which states that a DC current of 26 microampere flows through the circuit shown. Here we have a DC voltage source. This is the DC voltage source. And because of this DC voltage source, some amount of DC current is flowing. That is 26 microamp of DC current is already flowing through the diode, which is forward biased. How can I say that it is forward biased? Because the positive terminal of the voltage source is connected to the anode. The diode in the circuit is forward biased and it has an ideality factor of 1. So if you remember the Shockley's diode equation, we come across this term eta. So this is known as ideality factor. Its value is given as 1. At the quiescent point, the diode has a junction capacitance of 0.5 nanofarad Its neutral region resistances can be neglected. Assume that the room temperature thermal equivalent voltage, that is VT. So this is equivalent thermal voltage, which is equal to KT by Q, where K is the Boltzmann constant, Q is the charge of one electron, 1.6 into 10 power minus 19, T is the temperature. So if I substitute the Boltzmann constant and value of Q, 26 millivolt, this you should remember. For omega is equal to 2 into 10 power 6 radians per second, the amplitude of small signal component of the diode current is dash. This is the question. It was a numerical answer type question that was asked in GATE 2018. So this is a very unusual question. We don't find this kind of questions normally in the GATE examination. So they have applied an AC signal as well on top of DC. So the amplitude of the small AC signal is 5 millivolt. So we are supposed to find how much is the amplitude of the DC current. So already because of the DC voltage, 26 microampere is flowing. Because of this AC voltage, there will be a small AC current also flowing. So we are asked to find what is the amplitude of this small DC current that is flowing. The frequency is also given 2 into 10 power 6 radians per second. So let's solve this. First, I'll write the small signal equivalent model for the diode. The ideal equivalent, simplified equivalent model, what I wrote, those are valid for DC currents and DC voltages only, for the DC analysis only. For the AC analysis, to perform the AC analysis, first we should make sure that the diode is already forward biased. So the AC equivalent of the diode is something like this. If this is the diode, then the AC equivalent is something like this. We have a capacitor in parallel with a resistance. So this is the AC equivalent model for the diode, where Cj is the junction capacitance. Because a diode is a PN junction, we have P type and we have N type and a depletion region in between. So it forms a capacitor because of the charge suppression and the depletion region in between. So that is the reason why we are having a junction capacitance. Its value is given as 0.5 nanofarad. Okay, so let us try to solve. So let me write the AC equivalent circuit for your understanding. We will not consider the DC part because we know already that the diode is forward biased. So instead of diode, I'll use a capacitor and a resistor. Then we have a 100 ohm resistance in the circuit. This is the reference node, and input signal is 5 sine omega t millivolt. Okay, and this is Cj, this is Rd. So given Cj in the question, it is 0.5 nanofarad. IDC is already given. IDC is 26 microampere. VT is given 26 millivolt. Okay. Next, we are supposed to find what is Rd. So all the components are known except Rd. So we'll have to find what is Rd. You need to remember this equation. Rd is the diode resistance because of the DC current. So diode static resistance. It is given by eta Vt by Id. And eta value is 1. So if I substitute all the values here, 26 millivolt by Id is 26 microampere, I can find out what is the value of Rd, which is 1 kilo ohm. So this is RD. So next we are supposed to find out how much is the magnitude of the AC current. So magnitude of the AC current is given by magnitude of the voltage that is applied, 5 millivolt, divided by the total impedance of this particular part. What is the total impedance? So I'll write it as Z, magnitude of the total impedance. So how can I find Z? It's very easy. You can see here, this capacitor comes in parallel with this RD. This entire combination is in series with 100 ohm resistance. So I can calculate the impedance as 1 by j omega c. This is the impedance of the capacitor parallel with RD. This entire thing is in series with a 100 ohm resistor. So we can write 1 by j omega c as minus j by omega c. Omega is given in the question. It is 2 into 10 power 6. C is given in the question, 0.5 nanofarad. So if I substitute, I'll get minus j by 2 into 10 power 6 into 0.5 into 10 power minus 9. So this part will be equal to minus 1000 J. This is in parallel with RD. So RD is also 1000 whole divided by 1000 minus 1000 J. This entire thing is in series with 100. So using the calculator, we can find the value very easily. It will be 600 minus 500 J. So take the absolute value using your calculator, you will get 781.025 ohm. You have to be very careful. Don't try to round off the values because this is a numerical answer type. So most probably you will have to enter the value up to 2 decimal places accuracy. If you round off in each and every step, then the rounding error will accumulate and your answer will be way off. So substitute this value in the equation. So what I get is 5 millivolt divided by 781.025 ohm. So the value of IAC is 6.4 microampere. So this was a very different kind of question that was asked in GATE 2018. Rarely we find such questions asked, but you should know the AC equivalent or AC model for the diode as well along with the DC models. Okay, let's move on to the next type of question. So this is a typical question. This type of question, at least one you will get in every GATE examination. So this is a very typical question. So we have a diode here, which is in parallel with R1. A square wave is fed as the input, is applied as the input to this circuit. We are supposed to find what is the average voltage across the load. So VL is marked here. So we are expected to calculate the average load voltage. Once again, this is a numeric answer type question, and values of R1 and R2 are given. Both are 50 ohm each. Both are 50 ohm each. And please check here, the input voltage is going up to plus 8 volt in the positive half cycle, and it is going up to minus 10 volt in the negative half cycle. There is an asymmetry. So let us see how to find the average load voltage for this particular circuit. rewrite the circuit. So I'll rewrite the circuit. It is something like this. So we have the source voltage plus minus Vs. Then we have a diode. So we have the diode here, and a resistor is connected in parallel to the diode. Its value is 50 ohm. Then we have another resistor 50 ohm, and here we have the source voltage Vs. And voltage across this 50 ohm we are supposed to find out. Average voltage across this 50 ohm we are supposed to find out. And the input signal is plus 8 towards in the positive half cycle, minus 10 in the negative half cycle. This is Vs, and this is T by 2, and this is T. So that is the time period of the waveform. Okay, first let us find out when is the diode forward biased and when it is reverse biased. So let me take the positive half cycle. Okay, when during the positive half cycle, this side is positive, this side is negative. And you can see that the diode, this is anode part, this is anode, this is cathode. So cathode is connected to positive. Immediately, you can assume that the diode is reverse biased. When the diode is reverse biased, you represent the diode as an open circuit. So I can remove this diode from the circuit itself. And please observe what we have here is a potential divider network or voltage divider network. So we can have voltage divider networks like this as well. If you can apply the voltage divider rule properly, you can solve most of the analog circuits. So this is V, this is R1, this is R2. In a voltage divider network, we'll have one voltage source and two resistors, and voltage across the second resistor mostly we will take as the output. So it's very easy to find out the voltage across the second resistor. It is given by V into R2 by R1 plus R2. And if each of these resistors are equal, if R1 is equal to R2, then this will reduce to this particular form. Output is always the supply voltage divided by 2, half of the supply voltage. The same scenario is found here. So instead of writing the circuit like this, we can also write it like this. So we can have voltage, first resistor, second resistor, and I need voltage across second resistor. So this is same as this circuit. So it can be written like this as well. Even in this case, the output, the voltage across second resistor is V by 2. So the same scenario is present here in this question also. So what we have is a voltage divider network. So output voltage will be the supply input voltage divided by 2 because both the resistors are equal. So let me plot the graph. So for the positive half cycle, the output is half of that of the input. So it is 8 volt, half of that would be 4 volt. So this would be 4 volt till T by 2. Okay, fine. Next, let us see what happens in the negative half cycle. In the negative half cycle, so this side becomes negative, this side becomes positive, this side is negative, this side is positive. So negative is connected to cathode, and positive is connected to anode. So the diode is forward biased. How do we represent a forward biased diode? As a short circuit. whenever we have a short circuit across the resistor or any other component, so this is bypassed. This no longer participates in current conduction because this is the least resistance path. So the entire current will flow through this. So the output voltage will be minus 10 volt, no change in the output for the next half cycle. So this is minus 10 volt. We are supposed to find the average DC voltage. So how to find average DC voltage? You will have to integrate this entire waveform starting from 0. So this is V naught of t. You'll have to integrate this waveform starting from 0 to one complete period. Integrate V naught of t with respect to t and divide it by the period t. So this is how we are supposed to calculate the average or the DC voltage, but do not integrate. It is very time consuming. Since the output waveform is a square wave, you can directly find out the average voltage. If you perform integration, what you are going to get is the area under the curve. Since we have square waves, we can calculate the area very easily. So first let me calculate the area of this part. It's a rectangle whose width is t by 2, height is 4. So area of this part is 4 t by 2. And the area of the remaining portion is, its width is t by 2, but height is minus 10. Sign is important. So area of this part is minus 10 t by 2. Now we need the total area divided by t, that is the period. So total area is 4 t by 2 minus 10 t by 2. Divide this entire thing by the period, which is t. So 4 t by 2 minus 10 t by 2 is 6 t by 2, which is 3 t. Then divided by t. So you get, minus 3 t. You will get minus 3 volt. So the voltage, average voltage across the load is minus 3 volt. So the correct answer is minus 3 volt. This is a numerical answer type. And one question similar to this can be seen in almost all the GATE examination question paper. One more typical question that comes in the GATE examination is this one. This question was asked in GATE 2020. Once again, this was a numerical answer type. That means options are not given. You are supposed to enter the values. So you'll have to calculate this very carefully. Whenever you find this kind of circuit, you have two capacitors and two diodes connected like this. Okay, whenever you find such a circuit, this is nothing but a voltage doubler circuit. It's nothing but a voltage doubler circuit. Two capacitors, two diodes arranged in this fashion is a voltage doubler. So the output voltage is always the double of the input voltage, but we have the capacitor, it will be peak voltage. Okay, so let us see what the question is asking, what they are asking. In the circuit shown below, all the components are ideal and the input voltage is sinusoidal. So the input voltage is sinusoidal. The magnitude of steady state output V naught rounded off to 2 decimal places is dash is the question. So we are supposed to find out what is the output voltage. And input is sinusoidal, they are telling, but the voltage what they have specified is 230 volt. So this is 230 volt. So what is the peak? That is the RMS value. What is the peak voltage value? For sinusoidal signal, you can find peak voltage VP. The relationship between the RMS voltage and the peak voltage for sinusoidal signals is peak voltage is √2 times VRMS. VRMS into √2. So if I calculate the peak value, it is 230 times into √2, which will be 325.27. So this side would be 325.27 volt, and the minima, the negative most, will be minus 325.27. So from peak to peak, it will be around 650.54 volt. 650.54 volt. Peak to peak. This is the input. And they are telling diodes are ideal, capacitors are also ideal. So we don't have to worry about the values of the capacitors. Anyway, they have said that as ideal. So let us see how to find out. First, I'll tell you how to analyze it. You don't have to really remember. Just look at the circuit here. Just look at the circuit here. If you find two capacitors and two diodes connected in this fashion, it's an voltage doubler. You don't have to analyze it. But for you to understand, I'll show you the analysis as well. So first, let me rewrite the circuit. So what I have here is a capacitor, a diode, one more capacitor, and a diode here. This is V in, this is C1, C2, D1 and D2. And this is V0. We are supposed to find out what is the steady state output voltage. And input is, peak is 325.27 plus 325.27. This side is minus 325.27. Okay, this is a very typical question that is asked. Okay, whenever you get circuits like this, don't just analyze for one cycle. Whenever your question says steady state output, you try to analyze the circuit for at least 1.5 cycles. If you analyze it only for the first cycle, then you may lose, you may not get the proper answer. So you'll have to analyze it for at least 1.5 cycles. So I'll analyze like this. I'll take the input like this. Instead of just one cycle, I'll take the previous half cycle also. So this is V in. Okay. Initially assume that all the capacitors are discharged. Okay. So during the negative half cycle, during the first negative half cycle, this side is positive, this side is negative. Okay. When that happens, please see here, this diode D1 acts as, sorry, I wrote it wrong. This side is negative, this side is positive for the first negative half cycle. This diode D1 acts as short circuit, and because of that, current will flow like this. Don't think that, this side is positive, so diode D1 is forward biased, that positive will come here, D2 is forward biased. That is incorrect. If current flows like this, then it has no return path. It has to come back like this. So diode D2 is not forward biased. Diode D2 is reverse biased. It's not forward biased, it's reverse biased. So the current will flow like this. Capacitor starts to charge. To what value? To the peak value. What is the peak value? It is 325.27. With what polarity? Because it is charging in this direction, current is flowing in this direction. So this side becomes plus, this side becomes minus. Okay, this is the scenario for the first negative half cycle. So let us see what happens for the next half cycle. So this was the status of the diode. Okay, for the next positive half cycle. So this is positive half cycle. So this side is positive, this side is negative. This particular diode is reverse biased, whereas this particular diode is forward biased. So I'll represent this as a forward biased diode. And what is the peak voltage here? 325.27. And current will flow in this particular loop, charging capacitor C2. To what value it will charge? It will charge to the peak value, that is 325.27. From the previous negative half cycle, 325.27 volt is already there in the capacitor. So this capacitor discharges. Along with this, C2 will charge to a maximum of 650.54 volt. So this charges to a maximum of 650.54 volt. So that's the answer. Okay, but let's see what happens during the second negative half cycle. So as soon as the voltage starts to drop from its maximum value, immediately this diode becomes reverse biased. Okay, this is not forward biased yet, but this is reverse biased. And capacitor holds this particular charge as there is no other path for the capacitor C2 to discharge. So 650.54 is maintained. And the answer for this question is 650.54. So 650.54. So it charges to 650 and 650.54 volt and it is retained. And every half cycle, this C1 discharges. In the positive half cycle, in the negative half cycle, it charges with the polarity like this. So thereby we get doubled voltage. Peak is double. Okay, so this is the concept of voltage doubler. Let us see one more typical question that involves diode and a capacitor. Here a circuit is shown. A 10 volt square wave is applied to the input of the circuit. The period of the waveform is given. T is 4 millisecond. With R as 500 ohm and C as 10 microfarad. And capacitor is assumed to be initially uncharged. And the diode is ideal. So what is the voltage across the capacitor at time t is equal to 3 millisecond? Okay, so first important thing, during positive half cycle, diode is forward biased and the capacitor charges to some value, to some maximum value. This is a square wave. And after t by 2 seconds, the polarity will change. This side will become minus, this side will become plus, and the diode acts as open circuit. Diode acts as open circuit. Charging or discharging stops. Since the output is open, it is open circuit, capacitor cannot discharge. Current cannot flow anywhere. So it is going to retain this value, retain whatever value to which it has been charged in the previous positive half cycle. So the scenario is something like this. This is the input. Okay, so the capacitor charges during the positive half cycle, it charges slowly. Okay, and the moment negative half cycle comes, it is going to hold this value. Okay, the question is to what value, to what extent the capacitor will charge. If it charges to the peak value 10 volt, or is it charging to a value that is less than 10 volt and then it is holding. So what is that value to which the capacitor is charging? So that is the question. So we have 0 here. This is 4 milliseconds and this will be 2 milliseconds. Okay. The first point here is to find out what is the time constant of the capacitor, time constant of the charging. So that is given by RC. So R is 500. I'm very sorry for the interruption. There was some technical issue. Okay. So first we'll have to find out how much is the RC time constant. So RC time constant is 500 into 10 micro, which comes to around 5 millisecond. What this tells us is for capacitor to charge to the maximum value, that is 10 volt, to the maximum value, that is 10 volt, it requires 5 milliseconds. But we are applying the signal, we are applying the positive voltage only up to 2 milliseconds. That means definitely it wouldn't have charged to its maximum value, that is 10 volt. So this is not possible. And if you find that the RC time constant is less than 2 millisecond, let's say if by any chance you got the time constant as 1 millisecond, then you don't have to do the calculation in the first step. So at 1 millisecond itself, the capacitor would have charged to the maximum value and it will hold the maximum value. That is 10 volt. Then the answer would have been 10. But unfortunately, the time constant is 5 millisecond. That means it has not charged to its, not even close to its maximum value. So we'll have to find out how much is that value. So you should remember, in order to find that, you should remember the capacitor charging equation. For your benefit, I'll do a small derivation. During positive half cycle, what happens is the diode is forward biased, so it is represented as a short circuit. You don't have to do this derivation, but you should remember this. It's very basic, fundamental. So this is C, this is R, this is a constant voltage Vs. So I'll transform this circuit to the Laplace domain. So if I take Laplace transform of a constant, it is constant by S. Fine. So R as it is, then capacitor 1 by S into C. 1 by S into C. Okay, so once again, this is the voltage divider case. So I want to know what is the voltage across the capacitor VC. So VC of S is the main voltage Vs by S into impedance of the second impedance capacitor, in this case, plus R plus 1 by SC. So we can write this as Vs by S into 1 plus SRC. Okay, using partial fractions, I'll resolve like this: A by S plus B by 1 plus SRC. And if I calculate the values of A and B, I'll get A value as Vs and B value as minus Vs into Rc. So if I substitute Vc of S, I'll get as Vs by S minus Vs Rc divided by 1 plus SRC. So I'll try to take the inverse Laplace transform. So I'll rewrite it minus Vs Rc. I'll take Rc forcefully common in the denominator. So I'll get S plus 1 by Rc. And this Rc gets cancelled. Now I'll take the inverse Laplace transform. Vc of t is inverse Laplace transform of 1 by S is 1. So we have Vs into 1 as it is. I'll take the common factor 1. So inverse Laplace transform of 1 by S plus transform is e power minus at. So we have e power minus t by Rc. So this is the equation for capacitor charging. This is very, very important. You will have to remember this equation. So many questions in the GATE examination will have capacitors. So you'll have to remember this capacitor charging equation. Okay, so let's try to understand. The capacitor charges till 2 millisecond. We want how much is the voltage at 3 millisecond. But capacitor stops charging at 2 millisecond, and whatever charge to whatever value the capacitor has charged, the same value will be continued for 4 milliseconds. So in between also the same value is held. So if we find what is the value at 2 millisecond, that will be the value at 3 milliseconds, 3.5 millisecond and 4 millisecond also. So you don't have to find out the value at 3 millisecond because charging is happening only till seconds. So put Vs is equal to 10 and t is equal to 2 millisecond. What you get is 10 into 1 minus e power minus 2 millisecond divided by Rc. We have already calculated, it is 5 millisecond. So substitute using your calculate, find out, you will get a value of 3.29 volt. So this is the solution for this problem. So this is one very important problem. You will get similar problems in the GATE examination. So let us look at some more problems, but for the want of time, I'll discuss the very important problems only. So sometimes we get problems, questions related to this inner diode. Okay, one important thing about the diodes, whenever you have a diode connected in parallel to the independent voltage source, let's say V is equal to 10 volt, then the voltage across the diode will also be equal to 10 volt, whether it is forward biased or reverse biased. Whenever an independent voltage source is connected in parallel to the diode, it is always the independent voltage source that prevails. So it would be 10 volt. Okay. So if we have an independent voltage source like this, 10 volt, then we have some resistor and then some diode. Then voltage across the diode now depends on its state. Okay, we have a buffer resistor as well. So in this case, you will have to check whether the diode is forward biased or reverse biased. If it is forward biased, then the voltage across the diode is 0.7 volt if it is silicon. Okay, remaining voltage will drop across the resistor. But if you do not have any resistor here, then voltage across the diode is same as the voltage of the independent source. But here the diode can maintain its forward drop voltage. Okay, it has that flexibility. Why? Because independent voltage source is not directly connected in parallel to the circuit. The same thing happens with the Zener diode as well. Please keep this in mind. If the Zener diode is reverse biased like this, let's say it is 5 volt Zener diode and I have applied 10 volt, then voltage across this Zener diode, first of all, it is reverse biased, but don't make the mistake of telling that the output voltage is 5. It is not 5. Why? Because independent voltage source is connected across the Zener diode. So voltage across the Zener diode, even though it has entered breakdown region, is 10. Why? Because of the independent source. Okay, fine. Suppose I have a resistor here, then you can say it will maintain 5 volt because any remaining voltage can drop across the resistor. So that is the case here. So we have a circuit here. The Zener breakdown voltage is 6. So what is the output voltage? Zener diode is ideal. So voltage applied is 10 volt. Don't come to the conclusion that, okay, there is a resistor here, so voltage across this Zener diode should be 6 volt. So V0 is 6. It is wrong. The Zener diode will maintain 6 volt only if the voltage at this terminal is greater than 6 without the Zener diode. So first, do not connect this Zener diode. Find out what is the voltage at this point. The voltage at this point is nothing but you can find using simple voltage divider. So we have 10 volt and 1 kilo ohm connected. So these are the resistors. So voltage gets equally divided. So it would be 5 volt. Now please put the Zener diode now. This is a 6 volt Zener diode. The voltage applied is just 5 volt. So the Zener diode is definitely reverse biased, but it has not entered breakdown. So it cannot maintain 6 volt. Then the output voltage is 5. So that is the solution for this problem. So you can get this kind of questions. Instead of 10, if I had applied 14 volt, then without Zener diode, the voltage would have been 14 by 2, 7 volt. But the Zener has 6 volt. The moment I connect the Zener diode here, the voltage is 7, its breakdown is 6 volt. So Zener would have maintained 6 volt. Okay, that's how voltage regulation happens. So first remove the Zener diode, find out how much is the voltage. If it is greater than the Zener breakdown voltage, answer is the Zener breakdown voltage. If the voltage here at this point is lesser than the Zener breakdown voltage, then whatever value you have calculated, that will be the answer as in this particular case. So this you should be very careful. Okay, we'll take one last question on the diode circuits. This is a multiple choice question. So what they are asking is that what they are telling is the Zener breakdown voltage VZ is 20 volt and maximum current the Zener can handle is 60 milliampere. Okay, R1 is 1 kilo ohm and R2 RL is 200 ohm. Okay, input they have not specified. So what is the range of the input? What is the range of the voltage VI that will maintain the Zener diode in the on state? Don't go by this literal meaning of this on state. That means current should be conducting through the Zener diode. It is not on. It is more like conducting stage. Of course, in the reverse bias. So reverse breakdowns region. Okay, the typical region of operation for Zener diode is Zener breakdown region. So that is considered as on state for Zener. Don't take the literal interpretation of on as forward biased. Okay, then you will go wrong. So we'll have to find out how much is the what is the range of input for which the Zener diode will be conducting. So you can go from the options as well, but it is slightly tricky. At least one voltage we'll have to find out because the voltages are very far apart. None of the voltages are repeating here. If you find out one voltage, either minimum or maximum, you can select the option. You don't have to solve for the other one. But anyway, I'll show you how to solve for both the ends. So let me rewrite this circuit. Okay, let me rewrite this circuit. So what we have here is VI. Then we have 1 kilo ohm resistor. And then we have diode, Zener diode. Then we have 200 ohm. This is 200 ohm resistor. Okay. To maintain the constant voltage of VZ is 20 volt, that is specified. IZ maximum is 60 milliampere. Okay. So if this Zener diode is to be in the conducting stage, then the voltage at this point must be at least 20 volt, because that is the Zener breakdown voltage. So this has to be 20. And you have to set the input voltage in such a way that after voltage division, you will get at least 20 here. Okay, VA should be 20 volt. So we shall apply the voltage division. Forget about the Zener diode for a moment. So VA can be calculated using voltage division, VI into 200 by 1000 plus 200. So 20 equals VI into 200 by 1200. Sorry, I made a mistake. I made a mistake in the question also while reading. This side is 1000, this is 200. So VA is VI into 1000 by 1200. So VA is required is 20. So VI into 1000 by 1200. So VI should be at least 24 volt. So minimum VI required is 24 volt. If you check the options, you already know the answer. So minimum VI is 24. So option B is the answer. But how did I get, how do you get 36 volt? So I'll show that calculation. You might find it interesting. And if you get any questions related to that, you can attempt. So minimum voltage required is 24. If you make this 25, if you make this 25 also, VA is not going to change. Why? Because that is the Zener breakdown voltage. If you make it 27 also, VA is not going to change. Okay. So let us find out how much is the load current that is flowing. Because above 24 volt, this is always 20 volt. So I can calculate how much is IL. IL is nothing but 20 by 1000. So load current is always going to be 20 milliampere. So always it's going to be 20 milliampere above 24. Okay. So how much is the Zener current that is flowing? This is maximum allowable. So let us find out how much is the Zener current that is flowing. For that, I should know how much is the main current that is coming from the voltage source. So it is 24 right now. This side voltage is 20. So I is 24 minus 20 divided by 200. That is 4 by 200. So once again, it is 20 milliampere. So this is 20 milliampere and entire 20 milliampere is flowing through the load. That means current flowing through the Zener is 0. So what is the maximum current that can flow through the Zener? Till 60 milli. So Zener current can increase up to 60 milliampere. So in that case, this total current can go up to already 20 milliampere is flowing plus 60 milliampere. So it can go up to 80 milliampere. Okay. For what value of VI? I'll get 80 milliampere. That is the question now. So when do I get 80 milliampere? For some value of VI, this side it's always going to be 20 divided by resistor is not going to change. So you solve this, you get VI is equal to 36 volt. So that's how you get 36 volt. So the correct solution is this. So I'll skip this question. This is very much similar to the previous question. For the want of time, I'll not be able to take this question. But input is given, nominal value is given 6 volt, but 5% variation is there. So it can vary from 5.7 to 6.3 volt. So you'll have to find out how much is the value of resistor R and what should be the power dissipation of this, minimum power dissipation of this Zener voltage. To find out the value of R here, you'll have to consider 5.7 here, 5.7, and IZ minimum, they have said 2 milliampere should flow. And what is the value here that I get when the diode has entered is 5 volt. So load current is 5 milliamperes always. So the current that should flow here is 7 milliamperes. So for 5.7 volt input, 7 milliampere should flow, out of which 2 milliampere will flow through the Zener diode to keep it reverse biased and in the breakdown region, and 5 milliampere will flow through the load resistor of 1 kilo ohm, and 5 volt is maintained across the load. So what should be the value of resistor R? So R is given by 5.7 minus 5, that is 0.7 divided by 7 milli. So you will get the value of R as 100 ohm. There are two options. Next, how much should be the power dissipation? Okay, power rating of the diode. For that, you will have to consider the highest possible voltage, that is 6.3 volt. Now we know the value of R. This is always 5. So 6.3 minus 5 divided by 100 will be the current that is flowing. So that comes to 13 milliampere. Out of 13, 5 will flow through this 1 kilo ohm. So remaining 8 milliampere should flow through this Zener diode. So Zener voltage across Zener diode is Vz, which is 5 volt. Maximum Zener diode that will flow is 8 milliampere. So Zener diode's power rating should be Vz into Iz max. So if you calculate, you will get power as 40 milliwatt. So the correct option is option B. So this is similar to the previous problem, and this has come in GATE 2018. Let us move to the next type of questions based on BJT circuits. This type of question is also typical. This question has come in GATE 2020, that is last immediate previous year. An amplifier circuit is shown here. This is a direct coupled amplifier. As you can see here, input side, you don't have any biasing circuit or capacitor. Input is directly connected to the base of the transistor. So VBE is given, which is 0.7. KT by Q is given, that is 26 millivolt. Output resistance is very high and the base current is negligible. Okay, and all the capacitors are assumed to be short circuited. So we are supposed to find out how much is the voltage gain. Okay, always voltage gain in common emitter configuration is given by this minus RC parallel RL. If RL is not there, then it is just minus RC divided by lowercase RE. So this is the static DC resistance, small signal DC resistance of the diode, this base emitter junction. Okay, that can be calculated as 26 millivolt by IE. You know RC, you know RL. All you have to do is calculate how much is IE. Okay, that is very simple. That is very simple because this is direct coupled. For AC analysis, sorry, for DC, this IE is DC current. For the DC current, this is direct coupled. Capacitors are not there, so I can assume this as grounded. Okay, I'll use superposition theorem. I'll not consider AC at all. Now this is minus 10. We have VBE, which is equal to 0.7. So if I take the difference between these two, what I get is 10 minus 0.7, that is 9.3. So IE, you can calculate IE as 10 minus 0.7, that is the difference, divided by resistance, that is 20 kilo ohm. So I'll get the value of IE as 0.465 milliampere. So substitute this value here. So you'll get RE as 26 millivolt divided by 0.465 milli. So you'll get RE to be equal to 55.9 ohm. Okay, once you know RE, you know RL, RC, you can calculate the voltage gain. So RC parallel RL, that is 10K parallel with 10K will become 5000 minus 5000 because it is going to introduce a phase shift of 180 degree. RE we calculated just now, it is 55.9. So you will get the answer as minus 89.42. That is option A. So always for common emitter configuration, the voltage gain is minus RC parallel RL divided by RE. This is the model parameter. And RE can be calculated as 26 millivolt by IE. For any BJT you take, whether it is NPN or PNP, you'll have to remember these quantities. It has three components, three terminals: base, collector, emitter. This is base current, this is collector current, and this is emitter current. So emitter current IE will be always equal to base current plus collector current, and collector current will be equal to beta times base current. So substituting this here, so base current plus beta times IB. So I am substituting this here. So what I get is IE is equal to 1 plus beta times IB. So you'll have to remember this current equation basic, then this for any bipolar junction transistor. If they give you PNP, then the directions are reversed. That's it. And beta is known as current gain, common emitter current gain, that is IC by IB. Then we have one more parameter called as alpha, that is common base current gain. In that case, it is IC by IE. And always, if you can observe from this equation, IE will be greater than IC. So for a practical transistor, alpha will be less than 1. Alpha will be less than 1. And from this basic current equation, we can also relate alpha and beta. So alpha can be written as beta by 1 plus beta. Or you can also get beta as alpha by 1 minus alpha. So these are the equations that you need to remember. So you should not forget this. This can also be used. In case of an ideal transistor, sometimes they may say alpha will be equal to 1. If alpha is equal to 1, that means this value is equal to 1, means IE will be equal to IC. So whatever current IC you are getting, the same current will flow through IE. That means this current is not there. If this current is there, then it gets added up. So if IC is equal to IE, that means IB will be equal to 0. Okay, that is one thing you should infer if alpha value is given as 1. So this much at least you should know about BJT. See the next. This is very interesting. You will get a lot of questions like this. So this was asked in GATE 2020. Previously also they have asked similar questions. This is the internal, circuit of the voltage regulator. VI is unregulated input, that is 15 volt. And VBE we have to assume as 0.7 volt. So from here to here it is 0.7 volt. So from here to here it is 0.7 volt. And the base current is negligible for both the BJTs. If the regulated output is 9, this is also they are telling 9 volt, then the value of R2 is how much? Okay, don't get panicked seeing the circuit. It's very easy to solve. First check the output side. We have voltage, 2 resistors, and in between there is a tap. So it's a simple voltage divider. So if you know this voltage, I'll mark it as VA. You can relate V0, R1, R2 and VA using simple voltage divider rule. So what is VA? V0 into R2 by R1 plus R2. You know what is V0, you know what is R1. You are supposed to calculate R2. For that, you should somehow calculate how much is VA. So if you know what is VA, then immediately you can calculate what is V0. That is very simple. Please observe a Zener diode, a reverse biased Zener diode is always used as a constant voltage reference source in voltage regulator. So this is 15 volt. This is 15 volt. sufficiently large than 3.3 volt that is required to push this zener to the breakdown region. So we can safely assume that this zener diode is in breakdown region. So if it is in breakdown region, then it will have 3.3 volt across itself. So you can find out how much is the voltage from here till here. That is very simple. 3.3 volt plus 0.7 volt, because this is the voltage polarity. So 3.3 volt plus 0.7 volt will be 4 volt. So substitute 4 is equal to V naught, they have said 9 R2 by R1 is 1000 plus R2. So 4000 plus 4R2 is equal to 9R2. So take this 4 this side, you will have 5R2 equal to 4000, and R2 will be equal to 800 ohm. So very simple. So you should not leave this kind of question. So don't worry, don't get panicked, don't worry about all these components, how it works. It will work, it's used to maintain the change in the voltage, it provides the compensating current. So that those circuit elements are for compensating, that's it. Fine. So the voltage across zener diode plus 0.7 will give you the voltage at this point. Then it is a simple voltage division rule. Instead of this transistor, one can also use an op amp. So something like this. Don't get panic. It is very similar. So the output of op amp is there. We have minus, we have plus. So this is connected here. This is R1, this is R2, this is V0, this is Vi. And of course, this is connected here, and a zener diode is connected. This is connected here. Okay. So voltage across zener diode is Vz. So voltage at this point is Vz. So due to virtual short property, this point is also Vz. So here we get Vz. Then it becomes a simple voltage division rule. Whether they give transistor BJT here or op amp here, you'll have to find out what is the voltage at this point. Don't apply KCL, KVL, don't go for that. This is very simple. You'll have to just add the voltages, somehow reach this point. Okay, here in this case, this would be because of the virtual short. This is Vz. So this point will be Vz. So the answer for this question is 800 ohm. This was a numerical answer type question. So let us move to the next question. Okay. For the input Vin of T as shown in the figure, the transistor switches between cutoff and saturation regions when T is large. Assume collector to emitter voltage at saturation is 0.2 volt. So when the transistor is completely on, the voltage across this VCE is 0.2 volt. That is the saturation voltage. Base to emitter voltage is 0.7 volt. The minimum value of the common base current gain of the transistor for the switching should be. So they're asking alpha. What is alpha? So alpha can be calculated in terms of beta by 1 plus beta. And how do we calculate beta? We should know the value of IC and IB. So how can we calculate the value of IC and IB? It is very simple. The voltage applied is 2 volt. So this is 2 volt. So apply KVL to the input side. So what we get is IB, I'll directly write it. This is the base current IB. So voltage difference between this resistor is 2 minus 0.7. Resistance is 12 kilo ohm. So you can find out what is the value of IB. So IB value is 108.33 microampere. Okay, next job is to find what is IC. Okay, when transistor is on, voltage across this voltage across collector emitter, that is VCE, is 0.2. So current flowing through this 4.8 kilo ohm is difference in the voltage 5 minus 0.2 by 4.8 kilo, that is 1 milliampere. So we found out what is IC, what is IB. So put the values 1 milliampere by 108.33 microampere. So beta value is 9.23. Now put this beta value in this particular equation. So alpha is 9.23 by 10.23. So which will give you a value of 0.9. Okay, to whatever value, up to what precision they have asked, you'll have to calculate and round it off appropriately. So the value of alpha is 0.9. Minimum value of alpha is 0.9. Okay, this is a very straightforward application of equations which I had shown here. So you should remember these two equations. This is very, very important. This equation and this equation. So let's solve one more question related to the BJT. Okay. Consider the circuit shown here. Assume that VBE is 0.8 volt. They are telling this is 0.8. This time it is not 0.7, it is 0.8 volt. And alpha is unity. What this means is IB is 0. That means current is not flowing. IB is 0. Whatever IC you calculate, that will be same as IE. That is the meaning. The value of collector to emitter voltage is, so they're asking what is this voltage, VCE. Okay, so for that, first we'll have to find out how much is the emitter current IE. Because current flowing into the base is 0, we can use, see here, voltage source, 2 resistors. Once again, it is voltage division formula. We can find out how much is the voltage at this point. So how much is the voltage at that point? It is 18 into 16 kilo ohm divided by 44 kilo ohm plus 16 kilo ohm. That gives me a value of 4.8 volt. So from here till ground, till the reference is 4.8 volt. Out of which from this point onwards till here, from here to here, it is VBE 0.8. So from here to here, what is the voltage? Very simple. 4.8 minus 0.8, that is 4 volt. So voltage across this 2 kilo ohm is 4 volt. So immediately I can calculate how much is IE. It is 4 divided by 2 kilo ohm. So if I calculate that value, it is 4 divided by 2 kilo ohm. It is 2 milliampere. It is 2 milliampere. And because alpha is 1, IC is also 2 milliampere. You don't have to calculate. Okay. So what is the voltage from here till the ground? It is 4 volt. Now let us calculate how much is the voltage from here till this point. That is voltage across RC. So what I need is this voltage. We already know from here to here it is VCC, which is 18 volt. So I know the current flowing through this resistor 4 kilo ohm. 4 kilo ohm into 2 milliampere gives me voltage drop across that resistor. So which is 2 milliampere into 4 kilo ohm, which is 8 volt. So subtract 18 minus 8 is 10, minus 4 is 6. So voltage between these two terminals, collector and emitter, is 6 volt. That is 18 minus 8 minus 4. So VCE is 6 volt. And that is the solution. This question was asked in GATE 2017. So if you know that alpha is equal to 1, IC is exactly equal to IE and IB is 0, then you can apply the voltage divider rule this side. Okay, if IB is very large, then you cannot use this voltage division rule here to calculate what is VB and what is VE. You'll have to use Thevenin's equivalent circuit. You cannot do approximate analysis. Okay, let's move on to the next type of device, operational amplifier. So an operational amplifier will have an inverting terminal and a non-inverting terminal and an output terminal V0, and it is driven by supply voltages VCC and minus VEE. Typically, the output V0 can reach only up to the supply rails. Positive maximum output that we can get is either VCC or slightly less than VCC. That is known as V0 saturation. Towards positive, towards negative, slightly lesser than minus VEE. That is minus V0 saturation. And this op-amp amplifies the difference between its positive and its inverting and non-inverting terminal, multiplies that by this op-amp gain. So open loop gain of the op-amp is ideally very large. So output will either tend towards plus V0 sat or minus V0 sat. To control the gain of the amplifier, we introduce a negative feedback. If a positive feedback is introduced, the circuit becomes unstable. Sometimes that is used. A positive feedback circuit is also sometimes used. For example, in case of Schmitt trigger or in the oscillators, deliberately we will provide positive feedback and push the circuit to the unstable state. Sometimes that is required. Okay, the current entering these two terminals, are always assumed to be very less or negligible. And op-amp also has one property called as virtual short. Op-amp always tries to maintain these two voltages same. It tries to maintain, not necessarily say this VB I provide as 8. It always tries to maintain VA to be equal to 8. Tries to maintain. But it will not succeed always. Please bear this in mind. Okay, with this background, let us try to solve this problem. This is a very typical problem that is asked. Okay, it was asked in GATE 2018. The op-amp based circuit is implemented as shown below. Assume op-amp to be ideal. The voltage at node A, this is node A. What is the voltage at node A? Connected to the negative input of the op-amp as indicated in the figure. So they're asking what is the voltage at this point. Don't blindly say because of the virtual short, the voltage at this point and voltage at this point should be same. Because it is connected to the ground, it is 0. So voltage at node A is 0. If you say that, it is wrong. Okay, let us see why. Most of the times that will be the case, but in this example, it is wrong. Okay, let us see. First of all, this is an inverting amplifier. An inverting amplifier looks like this. Input voltage is applied to the inverting terminal through this resistor R1 and RF. RF is the feedback resistor. In this case, the gain will be minus RF by R1. This will be the gain, and output is gain times input. See, it is similar to the This is inverting amplifier. Instead of R1, we have 1 kilo ohm, RF is 31 kilo ohm. So the gain of this amplifier is minus 31 kilo divided by 1 kilo, which is minus 31. So input is 1 volt. So what should be the output? Minus 31 times input, which is minus 31 volt. So output required is minus 31 volt. But wait a minute, check with the positive and negative voltage supplies. See, at the max, the voltage can go up to minus 15 only. It can never reach minus 31 volt. So what happens is this voltage, the output saturates at minus 15 volt. It never reaches minus 31. Had this reached minus 31 volt, then here we would have got 0 because of virtual short. Because it is saturating, the voltage at this point is not 0. We will have to calculate. So it is not 0. So how do we calculate? We shall apply KCL at this node. Current going into this particular terminal is negligible because op amp is ideal. It is 0. So we can assume a current is flowing like this, I1. You can assume current flowing like this, I2. So what we can do is we can take this I1 is equal to minus I2. You can assume it to be in any direction, but appropriate sign must be considered. So what is I1? VA minus 1 by 1 kilo. So what is I2? Minus is already there. VA minus of minus 15 by 31K. So what we get is VA minus 1 by 1K is equal to minus VA plus 15 by 31K. So if I solve this, I get the value of VA as 0.5. So this is the solution, 0.5 volt. So whenever you are in doubt, always apply KCL at this particular node. Okay, don't go with the virtual short always. Okay, if the output is as expected minus 31, and if you have by any chance instead of minus 15 had they given minus 40 and plus 40 here, then output was minus 31, well within the limits, then we would have gotten this output. In that case, virtual short property will also holds good. So voltage at that point, node A would have been 0. But here, that virtual short property doesn't hold good because the output is exceeding the saturation limits. So you'll have to apply KCL to find out the value at node A. Okay, similar to this, many questions were asked in the previous gate examinations as well. So if you know this concept, it is very good. Let us take the next question. Okay, so this is also a numerical answer type question. In this circuit, all the components are ideal. Okay, if VI is 2 volt, what is the current I0 sourced by the op amp? So first check what is the output voltage. So this is a non-inverting amplifier. So always for non-inverting amplifier, voltage is applied to the non-inverting terminal and feedback is there. This is R1, this is RF. So output is related to the input as shown here, 1 plus RF by R1 times V in. So gain is 1 plus RF by R1. So let us try to find out the gain for this. 1 plus feedback resistor is 1 kilo. R1 is also 1 kilo. So gain becomes 2. So what is the output voltage? 2 times gain times V in. V in is 2. So 2 into 2 is 4. Is it within the range? Yes. Plus 5 to minus 5. 4 volt is within the range. So virtual short property holds good. So voltage at this point is 2 volt, that is given in the question. Okay, what is the voltage at this point? Because everything is within the range, this is also 2 volt. Next, we'll have to find out how much is the current I naught. So what is the voltage at this point? This is V naught, which is equal to 4 volt. Okay, so instead of directly trying to calculate I naught, we shall calculate how much is the current that is flowing here, I1, and how much is the current flowing here. So I naught should be equal to I1 plus I2 because it is the same current that is branching. So I naught is I1 plus I2. So how much is I1? I know this voltage. I know this voltage. Difference across this resistance, potential difference across this resistance is 4 minus 2. Resistance is 1 kilo. So I can calculate I1. Similarly, I2. So voltage across this resistance, that is V naught minus this side is 0 by 1 kilo. So it is 2 by 1 kilo plus 4 by 1 kilo. It is 2 milliampere plus 4 milliampere. So I naught will be equal to 6 milliampere. That's how you solve. So the current sourced by I naught is 6 milliampere. When calculating the gain, this resistor has got nothing to do. Okay, this is the feedback resistance that is directly connected to V naught and it is connected in the feedback path. So you'll have to consider only this resistance. So the solution is 6 milliampere. For the want of time, I'll not be able to take up this question, but it is very easy. This is a Zener diode. You know the operation of the op amp and the capacitors. So capacitor charges. Okay. So the question is, a unit step input is applied. Okay. What is the time t at which V out crosses minus 10 volt? Okay, that is the question. So I'll quickly try to solve this. A little complicated. So I'll write the circuit for your benefit. So the circuit is similar. Circuit is somewhat like this. We have the operational amplifier minus plus. It's an integrator. 1 kilo ohm. Then we have capacitor, another capacitor, and output voltage V naught. Capacitors are 1 microfarad each. Then we have a Zener diode whose breakdown voltage, Zener voltage is 2.5 volt. And an input of step is applied at time t is equal to 0. 1 volt is applied, it is held constant. This is input. So the question is, at what time t V naught crosses minus 10 volt? So initially it will be 0. Okay. So let us see. Let us see what happens. So I'll treat this as VA. Okay, because of virtual short, this is 0 volt. Okay, this is an ideal op amp. So supply limitation is not there. So always this virtual short property holds good. Once the input is applied, once the input is made as 1, initially capacitors are discharged. So current will start to flow in this path. And the capacitor charges. So Zener diode is not yet reverse bias because voltage across this capacitor is still 0. It will charge till the voltage across this capacitor, I'll call this as capacitor C2, capacitor C1. Capacitor C2 charges till its voltage reaches 2.5. Till this becomes 2.5, this charges. And afterwards, Zener diode will enter breakdown region and it will maintain 2.5 volt constant across this capacitor. Further charging of capacitor will not increase the voltage and it is not useful for us as well. So let us see at what time this charges to 2.5. For that, we'll have to find out how much is the current that is flowing. So to find out the current, I'll use this V in minus VA by 1 kilo, which is 1 minus 0 by 1 kilo. So current is 1 milliampere. So 1 milliampere current is flowing. So let me find out what is the voltage across capacitor. How do I find? Using this 1 by C integral 0 to T I dt. I of t dt, but I is constant because it is DC. So I'll have to integrate. So I should find out till what time, or what is the time required by capacitor C to charge till 2.5 volt. So I'll do this. I is constant, 1 milliampere outside, integral 0 to T dt. So which is 1000 into T minus 0, it is 1000. So I can this C2 takes 2.5 milliseconds. And by the time C1 would have been charged to 2.5 volt exactly. So it takes 2.5 milliseconds to reach to 2.5 volt. Once it reaches 2.5 volts, it's no longer charging. Okay. So the output voltage will be something like this, 2.5 volt. So this has to cross 10. So how much is still remaining? 10 minus 2.5, 10 minus 2.5, that is 7.5 volt is still remaining. So till what? 2.5 volt. C1 would have been charged to 2.5 volt at the same time. So it has to charge some more, 5 more volts. So by this time it is 2.5. So what should be the voltage to which C1 should charge? 7.5 volt. So it has to charge further 5 volt so that it becomes 7.5. So plus 2.5 becomes 10. So we'll apply the same formula. We'll apply this same formula to capacitor C1. Okay. So VC2 of T is equal to 1 by C integral 0 to T I dt. So for capacitor C1 to charge to 7.5 volt, how much is the time required? So integrate 0 to T dt. This is 1000 into T. So T becomes 7.5 millisecond. So the solution for this problem is it requires 7.5 milliseconds to charge. This was a little complicated, but you try to attempt these kinds of questions at the end. So these are high risk problems because they consume a lot of time. So try to attempt such type of questions at the end. So attempt the low risk questions in the beginning. Low risk questions are those questions which are based on the concepts that you have already learned in your engineering. Okay. So ones which are memory based or you already know the formula, those are low risk questions. So attempt those questions first. The last circuit what we are going to take is a Schmidt trigger circuit. For the operational amplifier circuit shown here, the saturation voltages are plus 15 and minus 15 volt. Okay, what are the upper and the lower threshold voltages for the circuit? That is the question. Okay, so we'll have to find out what is this. This is the threshold voltage, upper and lower. So once the voltage will be at 15 volt, Next time voltage will be at minus 15 volt. So it is a simple voltage divider rule. So let us try to apply. When V out is plus 15, how much is the current that is flowing? So I'll calculate I is equal to 15 minus 3. See, current entering this terminal I is 0, negligible. So the entire current I will flow through these two resistors. So I can directly write 15 minus 3 divided by total 10K plus 15K, 5K will be 15K. That will be 0.8 milliampere. So what is the voltage VTH? You can easily find out. VTH is V out, which is 15, minus voltage across this resistor. That is 0.8 milli into 10K. So first would be 15 minus 0.8 milli into 10K. That will give you 7 volt. So the answer is B. Okay, you can eliminate because plus 7 volt is there only in this particular option. So answer is B. So how did they get minus 3? Let us try to find out. When output is when V out is minus 15 volt. So I'll rewrite the circuit again. Okay, so we have minus 15. So I'll write the polarity like this, 15 volt. So we have 10K, we have 5K, and this is connected to the ground. Okay, so we have a ground point here. This is 3 volt. So I'll have to find out what is VTH. Okay, so what is VTH? So I'll find out how much is the current. So current will be 3 plus 15 divided by 15K, which will be 1.2 milliampere. So how much is VTH? VTH will be 3, and current flowing through this 5K is 1.2 milliampere. So 3, but the direction is like this. So it is minus 3 minus 1.2 milliampere into 5K. So that will give me minus 3 volt. So that is the solution. So finding upper triggering point and lower triggering point of Schmidt trigger is very important. You'll get questions related to this. So this was the question from GATE 2017. And this is a Schmidt trigger. And observe the feedback is given to the positive in non-inverting terminal. Okay, last question for this session. This is related to the MOSFET. Due to the lack of time, I could not take more questions on the MOSFETs and FETs, but FETs and MOSFETs are really easy. One important thing is you should know about the transconductance, that is equal to delta ID drain current by delta VGS. Okay, so this quantity is known as transconductance, change in the output current to the change in the input voltage. This is known as transconductance. Gain of a FET amplifier is always given as minus GM. If you have a FET amplifier being operated as a common source amplifier, it is always minus GM into RD, drain resistance. This is the gain. Anyway, let us see this question. In the circuit shown, there are two circuits given here. Threshold voltage of each NMOS is 0.6 volt. Ignoring the effect of channel length modulation and body bias, what are the values of Vout1 and Vout2 respectively? So they are telling the threshold voltage is 0.6. So voltage between gate and the source terminal, it will try to maintain 0.6 volt. Okay, so from here to here also again 0.6. Easily we can calculate how much is V out 1. So this, we don't have to consider this at all. So V out 1 is 3 minus 0.6 minus 0.6, which is equal to 1.8 volt. 3 minus 0.6 minus 0.6 is V out 1. Similarly, V out 2, 3 minus 0.6 here, but this has no effect on here. So 3 minus 0.6 here, this has no effect here. So, but this 3 minus 0.6 is 2.4 volt. So the correct option is option C, 1.8 and 2.4 volt. So this was asked in GATE 2019. Okay, please prepare on MOSFET circuits as well. You will be able to score good marks. Because of the lack of time, I'll be stopping today's session at this point. Thank you very much and all the very best. Thank you.